All right, on to number 13. Draw a pie chart of the saltwater versus freshwater in the world. All right, so we want to know that the amount of salt water in the world is around 97% of all the water, 3% for fresh. So if I'm drawing a pie chart to represent that, a very small amount would be from the fresh water. Very, very small amount. Of that 3%, what is fresh and accessible? The fresh and accessible is around 0.62% of all the water. And so if we said if there was about 3% total, we could kind of work out 0.62 of 3. What would that look like as a percentage? And so when we do that, 0.62 divided by around 3, it's somewhere around 21%, something like that. So around there. So graphically, just to give us a little different perspective looking at this, if I were to divide my pie chart into 4 equal parts, each part would be 25%. So 21% would be kind of most of one of them, something like this. And so this would be the area that is fresh and accessible of that water. All right. So keeping that idea about very limited amounts of fresh water in mind, we analyze the steps in the foul water lab. So I've got my water here. Initially, it was really dark brown. It had a bunch of stuff floating in it and sinking in it. And we put it through the sand gravel filter. And so what did it look like when we were done? It still was really dark and everything like that, but we removed all of these particles that were large. Maybe they floated, maybe they sank. So we want to really recognize here what change did we see. We would say the large particles were removed. So the large particles were removed in the sand gravel filter. All right. The particles were so large that they couldn't fit between the grains of the sand and the gravel. All right. Next, we put it through the charcoal filtration, and remarkable change happened. This is actually just what it looked like. It was clear and colorless. And it was odorless. So what this process did is that removed the odor and the cloudiness. We should note, even though we wouldn't be able to see this, that it was still conductive. Still conductive. So whatever is causing that conductivity, that was not removed. Then what we did is we did the distillation. And since we only had one thing to remove, that's what we're hoping to remove is the conductive particles. And so what we were hoping was that our water would not be conductive afterwards. All those particles that were causing the conductivity, they were left behind in the distillation process. Now, we didn't get rid of all the conductivity here just because it's very, very hard to do. But that's what that step would do. This is typically not done in the process at a water treatment plant in a big town because we don't want to remove everything out of the water. Some of the things that are in the water are actually beneficial for us. We actively put fluoride in the water for our teeth. We put chlorine in the water to kill bacteria. So we don't want 100% clean water. But this was just sort of to demonstrate the process of, can we do this? And if we could, how would it work? And that's the distillation part. All right. Next thing that we would draw here would be a solubility curve. And so we'll just draw a solubility curve. Temperature was on the x-axis. On the y-axis, we had our grams of our solute per 100 grams of water. And I'll just kind of draw like a generic solubility curve. If we were somewhere on the line, we would have a saturated solution. If we are below the line, we'd be unsaturated. And if we were above the line, we have two possibilities. One would be if I had some solid left over, then this solution would be saturated. If we heated it up and then cooled it back down, we could possibly supersaturate a solution. But if we have a data point sort of above the line, we have to know what the solution looks like to know whether or not it would be supersaturated or saturated. All right. How would each type of solution react to a change in temperature? So what I would do then is if I could maybe copy this, let's see if I can. Paste it over here. And I'm just going to remove my pictures for the moment. So if I had a saturated solution, how would it react to a change in the temperature? So if I had a saturated solution and I increased the temperature, then so if I had a saturated solution and I increased the temperature, it would then be below the line. It would become unsaturated. So the saturated would go to unsaturated. If I was unsaturated and I increased the temperature, it's going to remain unsaturated. Okay. If I had a saturated solution or a supersaturated solution and I'm above the line, we could stop here and be saturated, or we might go to unsaturated. All right. If I cooled these down, starting at the bottom with unsaturated, if I cooled it down, I could hit the line and become saturated if I cooled it down. If I had a saturated solution and I cooled it down, it would remain a saturated solution, but probably what would happen, it would remain saturated, but I would probably see some crystals precipitate out. All right. If I had a supersaturated solution and I cooled it down, not sure exactly what would happen. It really might depend on the chemical. It might stay supersaturated. At some point, though, it might get too cold and then turn into saturated and have all those crystals come out. All right. How would each of these react to an addition of an addition of some solute? So we can think about if we had clear solutions of each, and then we add one crystal to each. Well, if we had an unsaturated solution, we would expect our crystal to just dissolve, because the idea about an unsaturated solution is that it can dissolve more. If I had a saturated solution and we add that one crystal is just going to sink to the bottom and it will not dissolve. If I have a supersaturated solution, what's going to happen is that all that extra stuff that we tricked into dissolving will precipitate out of solution, and we're going to form lots of crystals. Lots of crystals, lots of solid are going to come out of solution. All right, on to the next video.